In this video lecture, we will be studying about the laser that stands for light amplification by stimulated emission of radiation. Light emitted from a laser has a very high degree of coherence and is almost perfectly parallel. Because of this high degree of coherence associated with the laser beam, it finds many applications like science and technology, medical, industries, defense, holography, spatial frequency, filtering, isotope separation, communication, and so on. In this video lecture, I am going to cover the derivation parts of the laser related things. Friends, you can see here that under the CSIR UGC NET for GRF and lecturership in the part B, section 7 in the atomic and molecular physics, it is asked about the lasers, spontaneous and stimulated emission, Einstein A and B coefficients, optical pumping, population inversion, rate equation, modes of resonators, and coherence length. So, in this video lecture, I will cover this topic on lasers. So, please stay tuned throughout whole of the video lecture because it is going to be very interesting for you. Let's start the video lecture. So, there are three main components of any laser device, and that are active medium, pumping source, and the optical resonator. So let's first understand the what is active medium. The active medium, also called amplifying medium, consists of a collection of atoms, molecules, or ions which is capable of amplifying light waves. Under normal conditions, the number of atoms in the excited energy state is always less than the number in the lower energy state. Light waves passing through such a collection of atoms would cause more absorption than emission, and therefore the wave will be attenuated. Thus, in order to have amplification, it is necessary to have population inversion between two atomic states in which the number of atoms in the upper energy level is greater than that in the lower energy level. I have discussed all those things in the Science World podcast in my other channel, so please watch that also for the clear concept about the population inversion and the pumping source. Now, the optical resonator. In lasers, an optical cavity or optical resonator is an arrangement of mirrors that forms a standing wave cavity resonator. Optical cavities are a major component of lasers surrounding the gain medium and providing the feedback of the laser light. So you can see here that there are two mirrors here. The first mirror is of high reflectivity and the secondary is the partially reflective. And this is the gain medium. Here we are pumping the energy with the help of the pumping source that maintains the population inversion in the medium. Now, the light confined in a resonator will reflect multiple times from the mirrors, and due to the effect of interference, only certain patterns and frequency of radiation will be sustained by the resonator, with the others being suppressed by the destructive interference. In general, radiation patterns which are reproduced on every round trip of the light through the resonator are the most stable, and these are the eigenmodes of the resonators. Resonator modes can be divided into two types. First, the longitudinal modes, and second, the transverse modes. In the longitudinal modes, the radiation differ in frequency from each other, while in the transverse modes, the radiation differ in both frequency as well as in the intensity pattern. Now, let us discuss about the Einstein coefficients A and B. This is lower level N1 and this is higher energy level N2. This is having energy E1 and this is having energy E2. And there are number of atoms in the lower energy level and there are few atoms in the upper energy level. And let N1 and N2 be the atoms per unit volume present in the energy levels E1 and E2 respectively if the radiation at a frequency corresponding to the energy difference E2 minus E1 falls on the atomic system, then it can interact in three distinct ways. First, an atom in the lower energy level E1 can absorb the incident radiation and be excited to energy level E2. The rate at which absorption takes place from level 1 to N1 to level N2 will be proportional to the number of atoms present in the level E1 and also to the energy density of radiation, that is H cross omega is equal to E2 minus E1. Thus, if U omega d omega is the radiation energy per unit volume between omega and omega plus d omega, then absorption per unit time per unit volume from level 1 to level 2 is given by the gamma 12 is equal to B12 U omega N1. Let us consider this is equation number 1, where B12 is the constant known as the Einstein coefficient of absorption, and it depends on the energy levels E1 and E2. And the second way of interaction is Einstein postulated that an atom can make a transition from energy level E2 to E1 through two distinct processes, namely stimulated emission and spontaneous emission. In the case of stimulated emission, the radiation which is incident on the atom stimulates it to emit radiation, and the rate of transition to lower energy level per unit volume is given by gamma 21, that is proportional to U omega N2, and which is equal to B21 U omega N2. And let us consider this is equation number 2. Now the third way of interaction is an atom which is in the upper energy level E2 can also make a spontaneous emission. This rate will be proportional to N2 only. That is U21 is equal to A21 N2. And let us consider this is equation number 3. At the thermal equilibrium between atomic system and the radiation field, the number of absorption is equal to number of emission per unit time per unit volume. That is number of absorption per unit time per unit volume is equal to number of emission per unit time per unit volume. Therefore, using equation 1, 2 and 3, we have N1 B12 into U omega is equal to N2 A21 plus N2 B21 U omega, implies that A21 N2 is equal to N1 B12 minus N2 B21 E omega. Therefore, U omega energy density is equal to N2 A21 divided by N1 B12 minus N2 B21, that is equal to A21 divided by N1 by N2 B12 minus B21. Thus, we have energy density is equal to A21 divided by N1 by N2 B12 minus B21. This is equation number 4. Now, using Boltzmann law, the ratio of population of the two levels at temperature T is given by N1 by N2 is equal to e to the power E2 minus E1 by KT, where KT is the Boltzmann constant and therefore N1 by N2 is equal to e to the power h cross omega by k b t, where e2 minus e1 is equal to h cross omega is equal to h nu, and Boltzmann constant value is equal to 1.38 into 10 to the power minus 23 joule per Kelvin. Hence, equation 4 reduces to energy density at omega is equal to A21 by B12 N1 by N2 minus B21 is equal to A21 divided by B12 e to the power h cross omega by kBt minus B21. That means u omega is equal to A21 divided by B21 whole divided by B12 by B21 into e to the power h cross omega by kBt minus 1. So we just divide the equation by B21 in the numerator and denominator. We get this. So this is the equation number 5. Now, according to Planck's law, the radiation energy density per unit frequency interval is given by E omega is equal to h cross omega cube n0 cube divided by pi square c cube into 1 by e to the power h cross omega by kt minus 1. So we will use this relation where n0 is the refractive index of the medium. So this is equation number 6, and using this relation 5 and 6 we get B12 by B21 is equal to 1, implies that B12 is equal to B21. Let's say it is B. This is equation number 7. And A21 by B21 is equal to h cross omega cube n0 cube divided by pi square c cube. This is equation number 8. Thus, we see that Einstein coefficient B1 and B2 are equal, and that is B. This implies that emission rate per atom is the same as the absorption rate per atom, and the ratio of spontaneous to stimulated emission coefficients is given by this value h cross omega cube n0 cube divided by pi square c cube. Now let us consider 1 by A is equal to Tsp, where Tsp is the spontaneous lifetime. Therefore, this equation reduces to B is equal to pi square c cube divided by h cross omega cube n0 cube into 1 by TSP. This is very important relationship for the Einstein coefficient B in terms of spontaneous lifetime T or 1 by A. The ratio of number of spontaneous emission to number of stimulated emission is given by R. The ratio of number of spontaneous emission to number of stimulated emission is given by R is equal to A N2 divided by B N2 U omega, and that is equal to A by B U omega. Let this is equation number 9 and this is equation number 10. So using the value of A and B from the equation number 9 and 10, we get R is equal to A by B U omega is equal to H cross omega cube N0 cube divided by pi square C cube into pi square C cube divided by N0 cube H cross omega cube into e to the power H cross by H cross omega by kt minus 1. We get e to the power H cross by kt minus 1. Let us take as this as equation number 11. So this is equation number 11. Now there are two cases. Case number 1. At some temperature capital T for omega very less than kt by h cross a by b u omega becomes very less than 1. That means a n2 will be very less than b n2 u omega, and then absorption emission lead. Now case number 2, if when omega is greater than kt by h cross a n2 by b u omega n2 is greater than 1, e to the power h cross omega by kt is equal to r, and this therefore in this case bu omega n2 will be very less than a n2, and in this case spontaneous emission dominate. So we see that for this condition omega less than kt by h cross, absorption emission when omega is greater than h, kt by h cross, in that case this will be greater than 1, and therefore this will be the case and spontaneous emission dominate. So friend, these are the things which I wanted to discuss with you. If you enjoyed this video lecture, please press the bell icon and press the like buttons and subscribe the channel if you are watching for the first time. And don't forget to share this video with your friends and colleagues so that they can also learn. Friends, in the next video lecture on the laser, we will be discussing about the relationship between the Einstein coefficient A and spontaneous lifetime of level 2 laser, and we will cover the line broadening mechanism, in which we will study about the homogeneous broadening. And inhomogeneous broadening, under inhomogeneous broadening, we'll discuss about the Doppler broadening, and the inhomogeneous broadening, we'll discuss about the natural broadening and collision broadening. And finally, we'll discuss about the laser rate equations. And if you are interested, we can also study the higher level laser system like three level laser system and four level laser system. So friend, stay tuned and watch the video lecture. Thank you.